Hey guys, in today's video we're going to go over the concept of collision theory. Collision theory describes what is needed for a chemical reaction to take place. Particles must collide with proper energy and correct orientation. This is called the quote-unquote chemistry home run. For example, in order for a batter to hit a home run, the ball has to collide with the bat. The bat has to hit with enough force to hit the ball far, and it has to hit the right angle so that it flies in the correct direction. We call this an effective collision. For example, in this picture, we have an example of an effective collision. This is because two particles or reactants are being collided together to form two new products, both being effective. An ineffective collision, as we see here, results in one product and two remaining particles that didn't collide. Therefore, it would be ineffective. Now let's go over the factors that ensure effective collisions between particles. The number one factor that ensures effective collisions is increasing the temperature. When increasing the temperature, molecules tend to move faster, energy increases, and therefore leading to more frequent collisions. While not all may be effective, the increased number of collisions means more chances for effective ones. Another factor contributing to effective collisions is increasing the concentration of a substance. When increasing the concentration, there is more molecules in the system. Therefore, the particles will have a higher tendency to react with one another since there's more of them. Next, we have increased surface area, and this only applies to solids. So, increased surface area allows more molecules to be part of the reaction. When there's more molecules in a reaction, there's going to be more effective collisions between particles. Last but not least, we have increased pressure, which only applies for gases. Increasing the pressure keeps the gases dissolved and able to react with one another. Lastly, we have introducing catalysts to ensure effective collisions because it provides a quote-unquote alternate reaction pathway, aka a shortcut for the reaction. This pathway will ensure a faster reaction rate, therefore more particles colliding with each other. In chemistry, potential energy is the energy stored in bonds or the ability of a substance to react. For instance, we have the scooter at the top of the hill, which has a higher potential energy due to its elevated position. This is similar to reactants in a chemical reaction that have stored energy. As the scooter moves downhill and reaches the bottom, most of its potential energy has been converted into kinetic energy. In a chemical reaction, once the products are formed, they usually have a lower potential energy than the reactants, with the excess energy released as heat and light in an exothermic reaction. Another key word that is important in creating potential energy diagrams is enthalpy, aka the heat of reaction. The heat of reaction is the total energy usage during a reaction that can be calculated by subtracting the potential energy of the reactants from the potential energy of the products. There are two types of reactions, an exothermic reaction and an endothermic reaction. An exothermic reaction is a chemical reaction that releases energy, usually in the form of heat or light to its surroundings. In this type of reaction, the energy required to break the bonds in the reactants is less than the energy released when new bonds are formed in the products. An endothermic reaction is a chemical reaction that absorbs energy from its surroundings, typically in the form of heat. In an endothermic reaction, the energy required to break the bonds in the reactants is greater than the energy released when new bonds are formed in the products. This results in a net absorption of energy, causing the surroundings to be cooler. Now let's begin drawing out our potential energy diagrams. On the left, you have the reactants, and on the right, you have the products of the reaction. At the top of this diagram, we have the transition state, also known as the activated complex. On the y-axis, we have the potential energy, and on the x-axis, we have the reaction coordinate. So notice that the products have less energy than the reactants. Whenever you see that, this reaction is considered to be exothermic, as we explained before. So whenever heat is released, the reaction is negative. As you see, the enthalpy is the difference between the potential energy of the products and the potential energy of the reactants. When you subtract reactants from the products, it's going to turn out to be a negative number since you're subtracting a larger number from a smaller number. Now, what is the energy difference between the transition state and the reactants? What is that called? This is known as the forward activation energy. Activation energy is the energy needed to get the reaction started. Without that energy, the reaction will not work. There's also a reverse activation energy, which begins from the product to the transition state. Now, what's going to happen if we add a catalyst to this reaction? Now we know that the purpose of a catalyst is to speed up a reaction by lowering the activation energy. As you can see here, by creating an alternate pathway, the activation energy is lower than what would be without the catalyst. Therefore, the reaction tends to go faster. So remember, a catalyst speeds up a reaction by lowering the activation energy. Now that we can draw an exothermic potential energy diagram, let's learn how to draw an endothermic potential energy diagram. So remember, in an endothermic reaction, energy is absorbed. Therefore, the products have to be above the reactants, and now it's endothermic. As you can see, the enthalpy, or delta H, is going to be positive since delta H is products minus reactants. And if you take a large number, subtract it by a small number, it's going to be a positive result. For example, if you subtract 10 minus 6, it's going to equal positive 4. Meanwhile, if you subtract 6 minus 10, it's going to be negative 4, and that would be for the exothermic reaction. So for an endothermic reaction, the enthalpy is always going to be positive. So let's put some numbers to these diagrams. So let's say the product is at a value of 100, the reactants is at a value of 300, and the transition state is at a value of 600. So if we want to calculate, let's say, the forward activation energy, the forward activation energy is the difference between the energy of the transition state and the energy of the reactants. So in this case, that's going to be 600 minus 300, so the activation for the forward reaction is positive 300. Now, if we wish to calculate the reverse activation energy, we have to subtract the energy of the products from the transition state. So that's going to be 600 minus 100, which is positive 500. Now, if we want to calculate the enthalpy, delta H, it's going to be the potential energy of the products minus the potential energy of the reactants. Products have a value of 100 and the reactant is 300. So because the products are in a lower energy, it's going to be negative 200, and that's the enthalpy for the reaction. Since the number is negative, we can assume that this reaction is exothermic. Now let's focus on heat energy. So imagine you have a metal rod, one side is hot and one side is cold. From what direction is the heat going to flow? Heat is always going to spontaneously flow from hot to cold. It requires no energy, and it just flows like that naturally. However, you can't get it to flow from cold to hot without an input of energy. Therefore, it would be non-spontaneous. Let's say we have a ball on top of a hill and it wants to roll down. It's going to be a spontaneous action because a ball can roll down a hill without any input of energy. It does it spontaneously. However, if we have the ball at the lower end of the hill and it wants to go up, you have to input energy into that action in order to push it up the hill. That would be non-spontaneous. Whenever you have a spontaneous reaction, it's going to have a positive entropy, higher disorder, because it happens naturally without any energy. while non-spontaneous reactions have negative entropy and require input of energy.